Welcome to this session of a small set of screencasts covering the fourth week in our time series analysis course. Today we will focus on the third part of regression-based models, particular exponential smoothing, and the transition from global to local trend models. And then at the end we will go for some operators and start getting to something totally different. So for now we have done model-based models covering all data so far. So one model fits all. In reality, well, sometimes there's no model that actually fits what we want to do. So what do we do in that case? That's the topic for today. We're going to make models that are not covering entire time, but just doing something that is local, or trying to find features as they are right now. So the first method is called exponential smoothing. Basically, you start off with a forgetting factor, which is a number between 0 and 1, and then you make a weighted sum of all your previous observations, where you use lambda to the time difference power j as weight. And we can write it out as a long sum, and in order for this to be a weighted average, we need the sum of the weights to be unity, and we get that by choosing the initial constant c as 1 minus lambda over 1 minus lambda to the n power. Now when n is large, c converges to 1 minus lambda. In particular, this goes fast if lambda is not too close to 1, and well, if lambda is too close to 0, well, basically then you have no information. So we'll get back to how to choose lambda in an optimal way. So when n is large, what we get is the exponential smoothing, the mean value for the end estimate is effectively 1 minus lambda as a multiplier, as a weight to scale to sum to 1, and then multiply on the scaled observations. Now if we take and split that after the first observation like this, then we can have 1 minus lambda times the most recent observation plus 1 minus lambda times all the previous observations. Now if we look at this parenthesis out here, what we see that we have lambda to some power, and if we move 1 lambda outside here, that parenthesis, then what we have in here is effectively like what we started out with for the definition of the local of exponential smoothing model. So if you compare this with this one down here, the only difference is that now we have n minus 1, whereas up here we start with n. So effectively what we have here is the previous estimate of the mean value, namely mu n minus 1. So what we have here is basically an update equation. Whenever you get a new observation, you take the previous estimate, multiply by lambda, and then you say 1 minus lambda times, and add 1 minus lambda times the newest observation. And you can keep doing that forever and ever. That also means, since we are estimating a constant, when you're predicting with it, no matter the prediction horizon L, the prediction will be constant. And we can also update predictions of whatever horizon. The formula is pretty much like the one on the previous slide. The only difference is now we have an L included here. When you get observation yn plus 1, you weight down the previous estimate by lambda, and then you have 1 minus lambda as weight on the most recent observation to get the updated based on observations up to time n plus 1, where previously was at time n. And that pretty much it for how to do exponential smoothing, except for how do we choose the lambda. But first, just to show you a different way of writing things, we define so-called simple exponential smoothing, where we just do the update as we did up here. The main difference is, well, we don't care about the initialization so much. We just start off with the first observation as the first Sn and take it from there. Whereas in exponential smoothing, you have to kind of do the weights all the way backwards in time. So for large n, we just define Sn as our estimator, and notice that the time is just shifted one lag down here. I could write it either way. We could also have Sn plus 1 here, and then it will be Yn plus 1 and Sn here. The important thing is that you have a previous estimate, you get a new observation, and then you get an updated estimate. Now, here we use lambda, named the forgetting factor. Sometimes you also say it's a smoothing constant, alpha, which is, well, what is here. So alpha gives you how much influence the most recent observation should have. Whereas lambda is how much weight do you put on your previous estimate. You can do both ways, and you will see both formulations in various settings. So it's just a matter of picking what you like. Now, I said I will get back to how to choose the smoothing constant. One way of doing it, and typical, is to say, well, we want to get good predictions. So we want to find, we look at the sum of square prediction errors for a given smoothing constant. We can also write it like this, using mu instead of the y hat formulation. It's the same thing. What we want to do is minimize S of alpha. So we want to find the alpha that minimizes this. And well, you can use numerical optimization, or you can kind of try some values and see what happens. That's not the core of this course. I will show you in a couple examples in a moment. Oops. So what you typically want to do, in particular if the dataset is large, then you want to kind of ignore the first part, because the prediction errors in the first part, where the model hasn't been trained properly, are typically larger, and some artifacts there should not be what makes you choose a particular value of alpha. So often you want to cut off kind of a burn-in period. How long a burn-in period you want to have depends on how much data you have. So I won't say, but I mean, disregard say 10% of your data, then you're still kind of having the bulk of information there. But again, it depends on the situation, what is better to do. Check it, see if it's sensible to that, and write down what you did. And what you should keep in mind is what the smoothing is used for. As in, if you want to do one-step predictions, you should minimize the one-step prediction error. If you want to do 10-step predictions, you should minimize the 10-step prediction error. It sounds obvious, but it's one of those things that makes life a little bit more messy at the end of the day. So an example of that, we have measured the wind speed 76 meters above ground level at the Risø campus, and we measure every 10 minutes, which means we do not expect the wind to change much from one sample to the next. But what we are asked to do is to predict 3 hours ahead using exponential smoothing. So here is data for about a year and a half, and you can see it looks quite volatile when you plot the whole thing all together. If we now evaluate S of alpha for, in this case, 10-minute prediction as in one step, and 7-step predictions as in 70 minutes, then what we see is that the optimal choice of alpha for the short-term prediction is to say, well, at least 0.95. That means put all your weight on the most recent observation. Pretty much just saying your prediction is that in 10 minutes it'll the wind speed will be the same as now. Now when you increase the prediction horizon to 7 steps, then the curve here is rather flat, first of all. You should also notice that the sum of square prediction errors, now that you're looking at 7-step predictions, is much greater than when you look at 1-step prediction, about a factor of 4 or even more actually. But the optimal value here is around 0.7, and you can see as it is, as flat as it is, there's virtually no curvature down here, then the exact value doesn't matter too much, but you need to get in the ballpark. Now if we increase to 130 minutes, what we notice is that it's still flat around the optimal value, but the optimal weight on the most recent observation is dropping. And when we go to 3 hours, that's 190 minutes, it drops even further to around 0.5, but still we have the weight as being 0.5 on the most recent observation, and then it's 0.5 square. This, as lambda is 1 minus alpha, it's 0.5 square on the second most, and then multiply by 0.5 every time you go backwards in time 1 step. So how does this work out? We'll just show this example where you look at the black line is the actual measurements, and then the 10-minute forecast. Remember, we're using a lambda or an alpha that is 0.95, which means we pretty much say that our estimate 10 minutes forward in time is the current value. And that's what you can see. Everywhere the 10-minute forecast is, and it's easy to see when the peaks are, is the same or almost the same value as the previous sample. And it's just slightly different from that. Now, if you go to a 190-minute forecast, basically what you observe is that the curve is shifted 19 steps, but you should also pay attention to how it's been smoothed out a little bit. Look, for instance, here, where the curvature is much smoother here than it is in the original data. And you also see that when you get up here to the top level, the plateau, the volatility is much less for the smoothened one than it is for the measurement and for the 10-minute data. Of course, this is, as you can see, when the wind speed is changing a lot within the prediction horizon. This is not a good forecast, but it is a forecast. And what we've done is to optimize it within this class of models, where the prediction is a mean value. And that is what should be kept in mind. For simple exponential smoothing, you predict a mean value. And that's all there is to that part of it.